Okay, picture this. It's 3:00 p.m. on a Friday. You've just deployed a new microservice. The code is beautiful.
Hmm.
I'm talking clean architecture, solid logic, all the unit tests are green, you're feeling good. But then real-world traffic starts hitting the endpoints. Heavy load. And suddenly, the dashboard just turns red.
Oh, no.
Latency spikes, throughput drops through the floor. You check the database, it's bored, barely doing anything. You check the network, totally fine. The culprit, it's inside the house.
The silent killer. The garbage collector.
It's always the garbage collector. Welcome back to the deep dive. Today we are looking at something that feels like it should be the most basic thing in programming, but it turns out to be a massive performance bottleneck: text processing.
Yeah, it's probably.
Specifically, we're digging into a fascinating article by Vineet Sharma, published just this month, February 2026. It's titled Mastering Zero-Allocation Parsers, a deep dive into high-performance C#.
This is a really significant piece of writing because it highlights a paradigm shift in how we handle data in the .NET ecosystem.
A paradigm shift?
Yeah. We're moving away from thinking of strings as just text values to display and starting to see them for what they really are: contiguous, readable memory blocks.
Contiguous readable memory. That sounds remarkably like systems programming, C or Rust. But honestly, I was surprised reading this. I mean, string manipulation. We've been doing string, split, and substring since, like, day one of learning to code.
It's muscle memory.
It is. How can something so fundamental be such a disaster for performance?
Well, it's the classic case of efficient isn't free. The modern garbage collector, the GC, is incredibly sophisticated. Sure, it's a marvel of engineering. But when you are processing gigabytes of data or handling thousands of requests per second, the convenient way of handling strings becomes a massive liability.
Okay, let's unpack this. The article starts with a really common example that I think every C# developer has written at least once: the configuration parser.
Oh, yeah.
You know the drill. You have a line of text, maybe from a config file, like key value, key to value 2. You need to make that up.
Right. It's the standard interview question approach. You have that string, you want to parse it. So naturally, what do?
I do line split.
Yes, sir.
It's one line of code, simple.
It looks so innocent. But let's look at what happens under the hood, in memory. When you call split, the runtime can't just know where the pieces are. It has to allocate a new array on the heap to hold the results.
Okay, so that's allocation number 1.
Right. Then, for every single segment it finds between the semicolons, it creates a completely new string object.
Okay, so if I have, say, 10 items in that list, that's one array and 10 new strings.
Correct. But you're not done, are you? Usually you loop through those results and you split them again. You split on the equal sign to get the key and the value.
Yeah, naturally. I need the data.
So now you're creating another array for every single pair, plus 2 more string objects for the key and the value.
Wow. Okay, let me do the math here. For one line of config, if I have n items, I'm looking at one initial array plus n arrays for the pairs plus 2 n strings. That's a lot of objects.
It's a cascade, a complete waterfall of allocations, and all of these are allocated on the heap.
And the heap is, well, we know it's the expensive place, but why specifically does this hurt us so much? These are just small strings.
They are small, yes. These objects are what we call Gen 0 or Generation 0 objects. They're short-lived. The GC is pretty fast at cleaning them up, but it still operates on a stop-the-world mechanism for parts of its process.
It has to pause my code.
It has to pause your execution threads to mark these objects as garbage and sweep them away.
So even if the pause is tiny microseconds, if I'm doing this thousands of times a second.
It adds up. It causes GC pressure. It's like, imagine you're trying to eat dinner, but for every single bite you take, you buy a brand new ceramic plate, put the bite on it, eat it, and then just smash the plate on the floor.
That is incredibly wasteful and loud.
It is. And eventually the floor is covered in smashed plates. You had to stop eating to sweep them all up. That sweeping time, that's your latency spike. That's why your application stutters.
The source actually mentions a JSON value extractor example too, which is probably even more common these days.
Exactly. Think about how often we parse JSON. Even a simple lookup, where you use Substring to pull a value out of a JSON string, triggers an allocation. You create a temporary string just to look at it, use it for logic, and then immediately throw it away.
Pure waste.
Pure waste.
So we have the diagnosis. The simple string methods are secretly resource hogs because they constantly allocate new memory. The article proposes a solution that sounds technical but promises to solve this: Span and ReadOnlySpan.
It's not just a solution, it's a fundamental new primitive in the language.
Mm.
This is the answer to our smashed plate problem.
Help us visualize this then.
Yeah.
If Substring is buying a new plate or maybe photocopying a page, what is a span?
Okay, think of it this way. Traditional string manipulation is like photocopying. If you want to read just one paragraph of a large document, Substring takes the document, runs to the photocopier, copies that paragraph onto a new piece of paper, and hands it to you. That new paper is the new string object.
Which takes time and materials and memory.
Exactly. A span, on the other hand, is like a window frame. You have the original document just sitting on the desk. You simply place a cardboard frame over it that only shows the paragraph you care about.
So you haven't created any new paper.
Nothing. You haven't moved the document. You're just looking at a specific slice of the existing memory.
I love that. So slicing a span creates a new view, not a copy.
Exactly. It creates a new view over the existing memory. No data copying happens. It's virtually free. The CPU just adjusts a pointer and a length integer.
And this all ties into the memory hierarchy, right? The source had some great diagrams about the stack versus the heap. I feel like as C# developers, we often just ignore this distinction.
We do because the language manages it for us. But to master performance, you have to understand the terrain. The heap is like a massive warehouse. It's great for long-term storage, but it takes time to log things in, find space, and eventually the cleanup crew, the GC, has to come in and organize it all.
And the stack.
The stack is your immediate workbench. It's right there in front of you, incredibly fast. It works on a LIFO basis, last in, first out. When you enter a method, you get space on the workbench. When the method ends, you just swipe your arm across the bench and it's instantly wiped clean.
No garbage collector involved at all.
None whatsoever. The cleanup is automatic and instant because it's tied to the execution scope of the method.
So the whole goal of Span and this zero-allocation philosophy is to keep as much as possible on that fast, self-cleaning stack.
Precisely. If we can process that config line or that JSON entirely on the stack using spans, the garbage collector never even knows the operation happened. It's invisible to the cleanup crew.
That sounds perfect. So why aren't we just using spans for everything? Why do strings even exist anymore? Why don't I just use span-char everywhere?
Well, there's a catch, or rather a set of very strict rules. Span is a special type called a ref struct.
The enforcer.
The enforcer, yes. Or the guardian of memory safety, as the article puts it, because spans point directly to memory, often on the stack. They have to live and die with that stack frame. If a span tried to point to stack memory that no longer exists...
Because the method returned?
Right. Your program would crash with a segmentation fault. Bad news.
So the compiler steps in to stop us from doing stupid things.
It has to. There are 3 big rules. First, they cannot be boxed. You can't convert a span to a generic object or an interface like IEnumerable. Object lives on the heap, and you can't put a stack-only item on the heap.
Okay, that makes sense. No casting to object.
Second, they cannot be fields in a class. A class lives on the heap in that warehouse we talked about. If you put a span which is tied to the workbench into a class in the warehouse, you've broken the safety model.
Great. The workbench gets wiped, but the warehouse still has a reference to it? Disaster.
Total disaster. You can't leave your window frame hovering in the warehouse when the desk is gone.
And the third rule, I feel like this is the one that bites people the most.
The async trap. Spans cannot cross await boundaries.
This is huge. We use async await everywhere in C# now. Why can't I use a span inside an async method?
You can use it inside it, but you can't hold on to it across an await. Think about how async works. When you await a task, the compiler chops your method up into a state machine. It pauses execution.
Right. It yields the thread back to the pool.
And to do that, it has to save the state of all your local variables so it can resume later. Where does it save them? It bundles them up into an object on the heap.
Ah, I see it. The compiler tries to move your local variables to the heap to survive the pause.
Exactly. And since ref struct types like span cannot exist on the heap, the compiler just screams at you. It physically cannot generate the state machine if a span is involved.
So spans are powerful, but they are strictly here and now. They're for immediate synchronous processing, not for waiting around.
Exactly. You fetch the data, maybe asynchronously, get it into memory, and then you hand it to a synchronous method to parse it with spans. You have to separate the I/O from the compute.
All right, let's see this in action. The source gives a real-world benchmark that I found really compelling. A log parser.
Yes, this is where the rubber meets the road.
So the scenario is we're parsing log lines. Something like 20260208 INFO system started. We need the timestamp, the level, and the message.
Okay. In the Before world, the heap-heavy world, we'd probably just use split on the spaces.
Right. And based on our earlier math, that's one array plus 3 strings. One for the timestamp, one for INFO, one for system started, plus the final login tree object itself.
The article estimates about 6 heap allocations per line.
Okay, now let's transform this using the zero-allocation approach. We create a log parser struct. How does it work step by step?
Instead of split, it uses index off. It just scans the memory to find where the first space is. It allocates nothing. It just gets back a number and integer offset.
Okay, so we have the position of the space. Now what?
Then, uses slice. It creates a window frame of the characters from the start up to that space. That's your timestamp. Again, zero allocation. Just a view.
But wait, don't we need to turn that timestamp text into a datetime object? Doesn't datetime parse need a string?
Here's where it gets really interesting. In modern .NET Core and onwards, the framework team has updated almost all the primitives. Datetime. Try parse has an overload that accepts a read-only span char.
No way.
Yes. It doesn't need a string anymore. It can read directly from the raw memory view.
That is so cool. So we parse the date without ever making the date string. We go straight from the raw memory to a datetime struct.
Precisely. Then we do the same thing. Slice the rest of the line to get the level INFO and the message.
But here is the part that I thought was the smartest trick in the whole article, the selective allocation.
Yes. This is the key takeaway.
Yeah.
It's not about zero allocations at all costs. Sometimes you do need a string. Maybe you need to save an error message to a database. You can't save a span to a database. The database is definitely in the warehouse.
Right. Eventually, data has to leave the stack and go live on the heap.
But the log parser is smart. It checks the level span. It compares the bytes directly to INFO. Since spans are comparable, this is super fast.
And if the level is INFO?
It just ignores the message, it parses the date, sees its INFO, and decides, I don't need to save this text. It allocates nothing for the message.
But if it's error?
Then, and only then, does it call toString on the message span to create a heap object that it can save.
So you're processing thousands of INFO logs with literally zero memory costs for the message string and only paying the price when you actually have an error.
Exactly. You're optimizing for the common case. And the results in the benchmark speak for themselves. They saw 8 to 10 times higher throughput.
And an 85% reduction in temporary allocations.
That 85% is the magic number. That's 85% less work for the garbage collector. That's where your latency spikes disappear. You stop throwing plates on the floor.
It's amazing. It's like we've been driving with the parking brake on this whole time, and Span just released it.
It really is. It changes the physics of your code.
I want to touch on some of the advanced patterns mentioned, because the rabbit hole goes deeper. The article talks about a URL parser.
Right. URL parsing is notoriously complex. You have protocols, hosts, query parameters, fragments.
And usually that means a lot of string splitting and object creation.
The advanced pattern here uses enum flags to track state. So instead of chopping the URL into little string pieces and storing them, the parser just keeps a parse state enum. Does it have a protocol? Set the flag. Does it have a query string? Set the flag.
So it's not storing the actual host string.
No, but when you asked for the host property on the parser,
It computes it on demand.
it computes it on demand. It knows where the host starts and ends. It stored the indices, so it just returns a slice of the original URL. It doesn't store the host as a separate string field at all.
That's so clever. It's lazy evaluation, but for memory. It creates the view only when you ask for it.
It is. But this brings up a really important question the article addresses. When do you use what? Because clearly we can't just banish the heap entirely. We aren't writing embedded C code here.
The decision tree. I like a good flowchart.
The rule of thumb is fairly simple. You just ask yourself, is this data small and temporary? Or is this data large and persistent?
Okay, so if it's small and temporary, like parsing a number or formatting a quick message.
Use the stack. Use span. You can even use stacklog if you need a tiny array of scratch memory. That actually allocates a byte array directly on the stack.
But be careful with stack-a-lock, right? You can't go crazy.
Oh, definitely not. Don't allocate megabytes there, or you'll get a real Stack Overflow exception. Keep it small.
And if the data is large or needs to stick around for a while,
Then you need the heap. But even then, you could be smart. The article mentions the array pool. Instead of creating a massive new array and throwing it away, you rent one from a shared pool.
the rent-to-center approach to memory.
Exactly. You say, hey, pool, give me a buffer. You use it, and then this is the most important part, you return it. Reduce, reuse, recycle.
There's some specific do's and don'ts that I think are worth noting. One big do is using value string builder.
Definitely. I use this one all the time now.
I know String Builder. It's the classic way to concatenate strings efficiently. What is value string builder?
Well, String Builder is a class. It lives on the heap. So even just creating the builder allocates memory. Value String Builder is a ref struct. It wraps a span-based buffer.
So you can build up a string like appending parts of that log message entirely on the stack.
Precisely. As long as the resulting string isn't huge, the whole operation stays on the stack. It's incredibly fast for things like formatting dynamic error messages or building cache keys.
Okay, and the don'ts. We covered the async trap, but there was one about dictionaries that seemed important.
The dictionary hack.
Yeah.
Don't try to outsmart the compiler on this.
Why would someone even try?
Well, say you parse that config file. You have a span for the key, say database timeout. You want to look that up in a dictionary. But dictionary string requires a string key.
And you can't use a span as a key because the dictionary lives on the heap.
Right. So developers get clever and try to hack it. They use unsafe code or weird casting. Just don't. If you need to use a dictionary, that implies storage and lookup. That is a heap activity. Just call toString on your span.
That's the price of persistence. You pay it when you need to store it.
Exactly. Don't fight the architecture. If it needs to be stored, it needs to be a string.
And the other don't was about returning stack spans.
Right. Never return a span that points to memory you allocated inside that same method using stack lock.
Because when the method returns...
The memory is gone. Poof. You're handing the caller a pointer to a location that is about to be overwritten by the next function call. It's a recipe for disaster.
The compiler usually catches this, though, right?
It does,
Yeah,
but
yeah.
in unsafe blocks, you're on your own.
So if we step back, this deep dive isn't really about never allocate memory ever again. That's impossible in a managed language.
No, that's a trap. It's about a partnership.
The stack heap partnership.
I really like that phrasing. The stack handles the journey, the processing, the parsing, the transformation. It's the highway, fast, moving, transient.
And the heap handles the destination.
Yes. The heap handles the storage, the persistence, the final result. It's the parking garage.
And we used to try to drive our cars inside the parking garage and park on the highway.
That is a chaotic image. But yes, we were using the heap for everything, clogging it up with temporary junk. Now, Span lets us use the highway for actual driving.
The article ends with a really powerful sentiment. The paradigm shift from everything is a string to strings are one representation of character data unlocks unprecedented performance.
It really changes how you look at code. You stop seeing text and you start seeing bytes and memory offsets. It's cleaner, it's safer, and it's vastly faster.
It makes me wonder, seeing how capable C# has become with these low-level memory tools, span, refstruct, stack-alloc, it raises an important question.
What's that?
We used to have this hard line. Managed languages like C# and Java are for business apps, and systems languages like C++ or Rust are for high performance.
Right. Safety versus speed. Pick one.
But if C# now allows this level of safe, high-performance memory management, does that gap even matter as much as it used to?
That is the million-dollar question.
Yeah.
When you can write code that is logically high level with all the amazing .NET libraries, but performs like low-level systems code, the lines get very, very blurry. You're getting the safety of a managed runtime with the speed of raw memory access.
Something to mull over for your next project. Maybe you don't need to rewrite that service in Rust just yet. That's it for this deep dive into zero-allocation parsers. Huge thanks to Vineet Sharma for the source material.
A fascinating read.
And thank you for listening. Go forth and optimize. We'll see you in the next deep dive.